Sorry.
Go ahead. Okay. Good morning. My name is William Newell, and myself and Bruce Nissan make up Team Purple, and I'll be talking today about the flow system, talking about the steady-state operating curve and the step response performance curve. Why do I even bother wasting my time doing this? To show measurements that have been made to analyze the steady-state operating curve and also to analyze the step response to observe some of the dynamic behavior of the system. To kind of go over a little bit of what I'll be talking about, I'll give a problem definition, which will go into a little bit of detail as far as the background, the customer, talk a little bit about the steady state, what we did for that, the step response, any plans, any future tests that we plan to be going on in the future, and Q&A again. The publicly owned sewage treatment company right here in Chattanooga, Tennessee has a large filter press which is used to help separate some of the solid waste from the liquid waste. Well, it operates in batches, like 1 big amount at a time, and in between those batches it has to be washed. Well, as per the manufacturer of the press, the flow rate of the nozzles that's used to actually wash the presses have to be maintained within 7 to 10 pounds per minute. This has a system diagram for the overall system, the input being the input driven into the centrifugal pump, or the motor that goes to the centrifugal pump that helps send the water through the whole system, and what we get as an output would be the wash water flow or the flow rate in pounds per minute. As far as steady state, first step we did as far as analyzing the system was to observe a steady state response out of this. And basically what we did was we let the system run long enough at a desired input until the levels of output reached at around an average value, which from there we were able to go ahead and take average and standard deviation, doing error analysis of it. The application to the problem, obviously this was the first step that we did in our analysis that will later help us determine what we need to do as far as fixing the problem. When the system was ran at 10%, this is what we got as output. This is what we would call complete garbage. So as far as it being used in future analysis, as far as the overall steady-state operating curve, this would not be considered. So as opposed to whenever the system was operated at 70%, as you can see, right after about 20 seconds, the flow level seemed to steady off, although the fact that the line is so thick can kind of hint at the response being kind of oscillatory, that the flow meter was not really, it was accurate, but it kept on reading up and down, and hence the reason of the thick line. It came out to an average for this particular input of 12.82 pounds per minute with a standard deviation of 0.264. From all the data taken, like I said, around 10%, I wasn't able to get it when the system started at 10%. I got garbage data, so I didn't include that to the steady-state operating curve. However, from all the inputs gathered, a relationship could be formed with C equaling 0.1 m plus 5.4 with an R-squared value of 0.99. The 0.1 m and the 0.54 are interesting numbers, as I'll get to with the step response. And with the step response function, that was to analyze some of the transient behavior of the functions. And as far as the application to the problem, it was the first step that we did in analyzing some of the dynamic behaviors of the flow system. What we ended up doing was we ran it at a particular input and ran it long enough for it to reach a steady state. Then after so long, we told it to increase its input by a particular percentage, which in this case was 20, and then we plotted the output and did our analysis on it. As you can see, delta M being the change in the input being 20%, delta C being the change from the general average of here to here, which, like I said, the fluctuation in values kind of indicate an oscillatory response, and I'll get into that a little bit later. The dead time was analyzed and the time constant was analyzed from noticing when the slope was made of the highest slope that was made of the response. And from there, we were able to calculate the time constant, the dead time, and the gain of the system. And we the middle ranges, the lower ranges, the high ranges of the entire system. Kind of what we came up with as far as the gain goes. Around the lower edges seem to have the most gain, but as the input levels were increased, the gain steadily declined. As far as the dead time goes, they were all necessary, as far as which dead time being the delay that it takes for the response to for the system to actually respond to the user input. They stayed relatively about the same, ranging from around 0.65 to almost 0.9. The time constant, as you increase your levels of input, the time constant increased. This is what we found in our system. Now, one thing interesting to note about it was, let me see if I can pull it up, was back in here, this is supposed to be the gain, because 0.1m is the slope of the input to the average output, which whenever we did the steady state, not steady state, but the step response for the gain, the only values that seemed to even hit around that level were the upper levels and the mid levels. The lower levels were not even close to it. So, as far as future testing goes, there's going to be a test to do some frequency testing of it, which all we're going to do is we're going to apply a sine wave to the system and see how that responds, which will give us a better idea of how the transient behavior of such a system. And we're also going to do some relay feedback to help us with our end goal, which will be to design a controller to help control the flow rates to where they'll be within manufacturer specifications of 7 to 10 pounds per minute.
Can you go back to where your time constant was?
Sure.
The pages from 0.5 to 1.3.
1.3. Right there. And oops. I guess, are there any questions about the system in particular?
You know what size filters they are?
Excuse me?
You know what size filters they are?
No, I don't. As far as our problem definition, the size of the specific filter wasn't given to us. All we were told was that one of it has to be made